Swayam Prabha. Digital India. Educated India.
So this is a continuation of our finite element equations in the solid mechanics by the variational approach. In this variational approach, as we were telling in the previous lecture, we are going to use the minimum potential energy, which is a very important variational principle from centuries. And in this, we formulate the potential of the body system. That is the internal energy. Internal energy is due to the elastic energy, elastic deformations, and then the work of external forces with a negative sign here. So this is, as I remind you, that this is the linear elastic solid mechanics. So, and then this is applied to linear solid mechanics. So the nonlinearity can be taken care in some other way later. So in this, we formulate the elastic energy to start with. Elastic energy is the multiplication of the stress and strain. So this is how it is defined. This can also be derived if you want. Is half sigma x epsilon x, and the 6 components are there and the 6 strain components are there, and it has to be integrated over the volume. Of course, there's a half here, so that when the body is loaded from zeroth state, so the potential is half of the final load multiplied by the displacement. And apart from that, we have the work of external forces, and which involves the body forces will take the body forces, and body forces will have the x bar, which is the intensity in the I direction, and y bar in the y direction, and z bar in the k direction. So this is like your weight acting on the body. And if you want to find out the work, it is the force multiplied by the displacement. So this is the intensity here. So that's why we need to integrate it with respect to the volume. So here I am using the integration signs V. Earlier we were using omega. So they are all interchangeable. And so this is the total expression now. The potential energy of the system consists of this elastic energy and together with the work of external forces. The work of external forces can also include the work of the traction acting on the boundary condition here, gamma T boundary. So that also can be taken care, just like we did in the case of weighted residual method. So let's, that can be included, but let us just see this one. This is for 3D, so we can simplify it for 2D. Let's do it for 2D. So we will take only the XY component. So that is, let's look at the internal energy to start with. This is the strain energy, so which is this part here. Of sigma x epsilon x and sigma y epsilon y and tau x y. Let's spend some time on this. So this can also be written in the matrix form in this manner. Epsilon x, epsilon y, gamma xy, multiplying sigma. Okay, we can write it in this matrix form. So this is the row and this is the vector. So multiplication will give you this product. Okay. So this first of all, let's look at this one, epsilon x, epsilon y, gamma xy. So this consists of so this stress strains are written in terms of the derivatives of the displacement. And here what we require is the expression for uv and w. So here what we do, so uv for, let's take the triangle element with 3 nodes. We'll take this one, and here so each node has a displacement 2 ui, vi, and so on. Okay, so what we do here, the displacement as usual, as in the previous cases, we express them in terms of the shape functions. I didn't write nkxy, and so similarly here. So shape functions multiplied by the nodal values. Okay, so this is the important part. So the u and v here are approximated by shape functions multiplied by the nodal values. Okay, so let's continue this one. So here this u and v can be written in the matrix form as Ni0, Nj0, Nk0, and multiplying ui, vi, uj, vj, uk, Okay, so these are the set of shape functions, and these are the nodal displacements. So we can write it. So this is as far as the displacements are concerned. So the strains are so using this. So these are the nodal displacements, just like here. And epsilon x is derivative of u with x, and this is what u. So this is dou ni by dou x times ui, dou nj by dou x uj, dou nk by dou x uk. And if you recall, this ni here is, recall, ni is ai diy. So using that, so if you take the derivative with x, so it will simply be I times ui, and then bj times 0 and bk times 0. So similarly for epsilon y, it is dou ni by dou y, so which gives you ci, okay, ci times vi, and cj times vj, and ck times vk. So continuing this one, similarly we get the shear strain ci, vi, vj, vj. So this is the strain in terms of the nodal displacement, and then this is the B matrix. We call this as a B matrix. So we'll write it as UE, which means that this representation we use for conciseness. So this is the elemental displacements here, that all the nodal displacements here are represented by this small simple notation. So this is B is the strain displacement relationship. Okay, so this is epsilon x, epsilon y, gamma xy. And then what else we need? We also need here sigma x, sigma y, tau xy. So that we simply write it as we also have sigma x, sigma y, is d multiplied by okay. So this is the constitutive equations, okay, between stress and strain, and this is how we write. So if you want this one, so this in terms of nodal displacements, so that also we can write as P times. Okay, so remember here UE . Okay, so this is almost everything is now expressed. So this, we know now the stress in terms of nodal displacements. And of course, there's a strains here, which are also in terms of nodal displacement. So let us put it in this one. Let's go back to this one and using this. So we have epsilon x, epsilon y, gamma xy in the rho form. So whereas here we have this in the volume of the element, and here we have half. So this is the strain in the column form, which we make it into a row form, and multiplying the stresses here, and stresses also will be d times b . Okay, so this is how that complete the strain energy will be. So this is the strain part, right? So which is the transpose here. So let us, this is a transpose of this one will be, if you expand this one, so that UE comes out. Let me take, this is volume of the, so will that be transpose D . Okay, so what we did here is that we collected all this P transpose dV inside, and we took out these nodal displacements outside the integral sign, because as far as the integration of this is concerned, so these are going to be constant. So UE, the nodal displacements are constant, so that's why we can take them out. So this we can also write it. So this we write as K okay, where K is the, interestingly here, this is called the stiffness matrix, so which is B transpose dB . So this is a two-dimensional thing, in which case we can say that, okay, if it is a plane stress, so you have a thickness also, in which case we can write it as T times area. And you can see one interesting thing, that this B matrix, which is strain displacements here, so this is the B matrix. So if you look at this one, for this three-noded triangle, this turns out to be constant, and so you can, so here B is constant for three-noded triangle. Okay, so once you observe that, so we can take out and this volume is nothing but area multiplied by thickness. So this thickness, if you want, you can use it as it is for plane stress, or you can take it to be unity in the case of plane strain. So the same thing we also should do for the case of the method of weighted residuals, the LR approach. There also we require the thickness multiplication. Okay, wherever you find the evaluation of the forces, okay, So then you have to multiply with the thickness also. So please keep that in consideration. And here it's very clear. So this is another important fact here, that this B being constant means that, so whatever be this nodal displacement, the strains anywhere within the element, right? So these are all supposed to be a function of xy, all of them. But here for this three-noded triangle, this turns out to be constant, which means that the strain anywhere within the element is constant. It's all same. So that is why this element is sometimes called the CST. So this element is called constant strain triangle. So as P matrix is constant, this is only true for the three-noded for this three-noded triangle. So B is constant. So epsilon comma xy are constant in the triangle. In the triangle. Okay. So that's why this is called, therefore this is called constant strain triangle. So which CST is called a CST, essentially due to strain being constant anyway within the element. So this is true for the three-noded triangle. Okay. So tomorrow you might do some other type of element, a six-noded triangle, in which case this is not true. Okay. So we have calculated now the stiffness matrix KE as B transpose dB integral, but it turned out to be constant here, just multiplying with the area. Okay. So in fact, this is exactly the same as your earlier approach, the method of weighted residuals, where we had Kij. So this Ke here is same as earlier obtained by, you can check it, obtained by method of weighted residuals. Okay, where we had all those Kii, Kij. So we had a 2 by 2 matrix, all those 2 by 2 matrix put together told you that it is a 6 by 6. So here also, this is also 6 by 6. Of course, you can see that B is 3 by 6, this is D is 3 by 3, and B transpose is 6 by 3, and together it is a 6 by 6. Okay, so you can observe that. So you can also check that this is exactly the same as the earlier obtained by method of weighted residuals. So it is obvious, right? Whichever approach you take, so you should get the same matrices. So here we call it as stiffness matrix. So apart from this, now we have other work of external forces. So let's look at this one. So this is now x bar u plus y bar v and again integrated over the element, which can be written as a row matrix UV multiplying X bar. Okay, so UV is it is n times nodal displacements. So here this can be written as and transpose of that, right? UV and multiplying X bar. Okay, so this is over volume of the element. Okay, so simplifying this further. Okay, so let's simplify it. So this is n times u and taken a transpose. So when you do the so it is UV transpose and transpose X bar Y bar. Right? Okay, so this is how this is. So we took a transpose, so that's how it is. And this can be simplified as UE transpose here. And okay, so let's so we took this UE transpose outside this integral sign because it's constant as far as the integration domain is concerned. So this is N transpose here will be N1 into N1 N2 sorry I J K this is N transpose. So multiplying X bar okay, so this is nothing but let us say that this is F where Fe is nothing but this one. So this is a 6 by 2 multiplying 2 by 1. So it becomes 6 by 1. Ni X bar, Ni Y bar, Ni X bar, so this has to be integrated over volume. Okay, so this will turn out to be what? So Ni, and in this, so this is Ni is Ni xy, and X bar, if you take it to be constant, so it is nothing but the integral of Ni over the area of the element, and of course the thickness comes here. So Ni over the area, so it is all A by 3, right? So A by 3 times x bar, y bar A by 3 So this is because the integral of Ni over the area is, so we can also use, as I was saying, that we can use the thickness T here, right? So this is the work of external force, which is UE transpose F, where F of the element is given by this one. So this is as far as the body forces are concerned. And let's continue this in our next lecture. Okay, so we are almost towards about to finish this one, but still there are a few issues here which we need to keep in mind. So let us stop it here for the moment, and we'll continue this one in our next lecture. Okay, bye for the moment.